So this video we are mainly going to talk about polarity of a molecule, and this polarity will base on the molecular geometry. And basically you know that polarity of a bond, which we learnt earlier, depends on electronegativity, and hence the polarity of a molecule will depend on the placement of these polar bonds. Let's go further and learn how these polar bonds influence the polarity of a molecule. We have learnt about electronegativity earlier, and you know that it is a tendency of an atom to attract the shared electrons in a covalent bond towards itself. Why I am repeating this again? So when a molecule is formed, it is these bonds which gives polarity to the molecule. And we also know that an element with a higher electronegativity attracts the electron towards itself. So in a molecule, if two atoms share it, the bond will be polar. And we also know that electronegativity increases in a period and electronegativity decreases in a group. And some of the most electronegative elements, I've just mentioned it there. Fluorine, oxygen, nitrogen are the most electronegative elements, and chlorine and nitrogen are almost same, followed by bromine, carbon and hydrogen. You don't have to memorize this, but keep it in mind that fluorine, oxygen, nitrogens are very highly electronegative. It will be useful later also. Let's see how this electronegativity and how do we determine the polarity of a molecule. Consider the molecule carbon dioxide, CO2. The Lewis structure, we have done so much of Lewis structure, you can draw the Lewis structure now. The Lewis structure of carbon dioxide is given there. And we know that oxygen is more electronegative than carbon. So because of that, the oxygen will be pulling the electrons more towards itself. And looking at the arrows, you can see that there are two equal forces acting in the opposite direction, and hence they cancel each other. And therefore this molecule carbon dioxide will be non-polar. So the bond CO in carbon dioxide is polar, but there are two forces acting in the equal forces acting in the opposite direction, and hence the molecule becomes non-polar. With that example of carbon dioxide, let's have some basic hints to identify a non-polar molecule. The first one, the molecule should have same atom as surrounding atom, and the molecule should not have a lone pair. Now, the electron domain geometry of the molecule is either linear with the same surrounding atom or trigonal pyramidal. I'm talking about the electron domain geometry and not the molecular geometry. Tetrahedral or trigonal bipyramidal, and you know the fifth one, octahedral. And you can see that the examples given over there have one central atom and the surrounding atom is same. So that is an important condition, and in none of these will have a lone pair. So the absence of lone pair is an important stuff, and the same surrounding atom is also an important concept. So these molecules which are perfect electron domain geometry without a lone pair will be non-polar. So just now we said that most of the perfect molecules are non-polar. So what are the molecules which will be polar? So molecules with more lone pairs will be polar. The example given there, water, 2 lone pairs is polar. Ammonia, 1 lone pair will be polar. And HCl2, 2 lone pairs will be polar. And SF4 with 1 lone pair will be polar. And I've given another example, ClF3. It has 2 lone pairs, so none of these molecules are symmetric, and hence the presence of the lone pair makes them polar. And is it always true that if lone pair is there, the molecule will be polar? One thing I said that if it has a symmetric arrangement like a perfect shape, like a linear, tetrahedral, etc., it will be non-polar. Then I said that if it has lone pair, it will be polar. But is there a situation when lone pair is present and the molecule is non-polar? Let's go further and see, do we have such molecules also? So when is a situation when the molecules have lone pairs and they are non-polar? So in some molecules, it's possible that lone pairs are positioned in such a way that they cancel each other and the molecule becomes symmetric. and that molecule will be non-polar. For example, consider the example of XeF2. XeF2 has 2 bonds pairs, F and F, and 3 lone pairs. And when I look at the electron domain geometry, it's trigonal bipyramidal because AB5 molecule. And the molecular geometry comes as linear. Bond angle is 180. So let me look at how these bonds and the lone pairs are positioned. So if you look at the second figure, I have shown how the lone pairs are positioned. The lone pairs are positioned in the triangle at an angle of 120 to each other, and they cancel each other. And the fluorine XeFe bond is polar, but it is again 2 equal forces acting in the opposite direction, hence they cancel each other. And therefore the lone pairs cancel each other, the XeFe cancels each other, and the molecule becomes symmetric, and hence XeF2 will be non-polar. So one case where the presence of lone pair doesn't make the molecule polar. Let me do one more example, XeF4. So as always, draw the Lewis structures, and you see that it has got 4 atoms and 2 lone pairs, and hence the type will be AB6. 4 atoms, 2 lone pairs, AB6. So the electron domain geometry will be for an AB6 is octahedral. Now molecular geometry with 2 lone pairs and 4 bonds, it will be square planar. So now look at the way these lone pairs and bonds are arranged. Look at the second picture. You can see that the 4 bonds are on the on the 4 corners, and even if the XeF bond is polar, they will cancel each other. And the 2 lone pairs, they are also positioned in such a way they are linear to each other, or they are at an angle of 180 to each other. So they are also 2 equal forces acting in the opposite direction, so they will also cancel each other. So basically the molecule XeF4 is symmetric, and all the bonds, in spite of it being polar, will cancel each other, and the molecule will be non-polar. So now we consider lone pairs for polarity. Now the next thing, most molecules with different surrounding atoms will be polar. CH4, same surrounding atom, therefore it will be polar. But if one of the hydrogen is replaced by a Cl, it will become polar. Or if I replace 3 hydrogen by Cl, CHCl3 will also be polar. Same way, if we consider PCl3, same surrounding atom, therefore the molecule will be non-polar. If I replace the hydrogen Cl with a hydrogen, this molecule will become polar because the surrounding atom is not same. And PHBr3, instead of chlorine, if I change it with a halogen, then also the molecule will be polar. And PCl5 will be non-polar, all the same surrounding atom. PHCl4, one of the Cl is replaced by the hydrogen, therefore it will be polar. And SF6 will be a perfect octahedral molecule, and therefore it will be non-polar. But however, I replace one of the fluorine with the any other halogen or hydrogen, the molecule will become polar.